तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Alright, so let me start by answering this question I had posed the last time, namely statement that a matrix L which has a set of eigenvalues lambda 1, lambda 2, etc. In the 2 by 2 case we discovered that these eigenvalues which control the behavior of a linear dynamical system were determined by just two combinations, the trace and the determinant of L. And the physical reason was that the eigenvalues are independent of this similarity, they are invariant under similarity transformations, and I will explain what this has to do with the way the dynamical system looks as a function of time. But before I do that, I would like to answer this question I had posed the last time: what would be the corresponding analog for an n by n matrix? If you have an n by n matrix, and the dynamical system is x dot is f of x, and this is linearized in the vicinity of a critical point, which let me take to be the origin, for example. This is linearized near the CP at x equal to 0, and this goes to L times x, where L is the Jacobian matrix. And the question is, if L has eigenvalues lambda 1, lambda 2 up to lambda n, then the solution to this equation here is generally each component of x is going to be a linear combination of e to the power lambda I t, where I runs from 1 to n, and depending on whether the lambda i's have positive real parts or negative real parts, the flow is going to be away from the critical point or towards the critical point, and we can start defining stability, asymptotic stability and instability. So the question is, what does it depend on? What do the eigenvalues depend on? What invariant combinations do the eigenvalues depend on for the n by n matrix? For the 2 by 2 we saw that it depended only on the trace and the determinant. What does it do for n by n? Any guesses? What should it be? What would it do? Well, cofactors, not quite, not quite. Remember, these eigenvalues have to be independent of making a similarity transformation on L. So if you change L to L prime, which is S L S inverse, where S is a non-singular matrix, the eigenvalues shouldn't change. The trace, yes, it will certainly depend on the trace, because the trace doesn't change under this, nor does the determinant. But what else? You need n of these combinations.
Trace of L square or something.
The trace of L squared, and then L cubed, yes indeed, that is true, that is the answer, because these are invariant combinations. Because suppose you pretend for a minute that you can diagonalize this matrix. Now once you have diagonalized it, the matrix looks like lambda 1, lambda 2, lambda 3 and so on, and the matrix squared looks like lambda 1 squared, lambda 2 squared and so on. The cube looks like lambda 1 cubed, lambda 2 cubed, and the sums of all these combinations are independent of making a similarity transformation. So the linear combination, the invariant objects, these things depend on T1 equal to trace L, T2 equal to trace L squared, Tn equal to trace L to the power n. Those are the combinations. I leave it to you as a trivial exercise to show that in the 2 by 2 case you can always write the determinant in terms of trace L squared and trace L, the whole squared. You can always write AD minus BC in that form. So the determinant was a bit of a red herring. These are in fact the invariant combinations. Now what is the meaning of saying that it is invariant under similarity transformations? Let us look at the 2 by 2 case. We saw that, for instance, let me take a simple example. We took an example where you had x dot equal to x, y dot equal to minus y, for instance. This was a saddle point because it is already in a diagonal form, and the critical point at the origin is a saddle point because the eigenvalues are +1 and -1, two real eigenvalues of opposite sign, and you immediately have a saddle point. Now what do the phase trajectories look like? Well, here is x and here is y. Things are going to flow in the y direction but flow out in the x direction, and therefore this is what the trajectories look like, and this was a saddle point. Now of course in the more general case you do not have something where x and y are decoupled in this fashion, but you really would have something which looks like x dot equal to ax plus by, y dot is cx plus dy, and we assume that the matrix A, B, C, D, if it has one positive eigenvalue and one negative eigenvalue, you have a saddle point very similar to this picture. But the flow is not going to look like this, it is not going to look like this at all, it is going to look a little more complicated, and my assertion is that it is just going to be a distorted version of this in here, because you see in principle I could always change variables. I could call u equal to ax plus by and v equal to cx plus dy, and u and v are linear combinations of x and y, and therefore in the uv coordinate system you would have very simple equations of motion. But what do u and v look like in the xy coordinate system? Two straight lines. So in the xy plane this could be the straight line u equal to 0, and this could be the straight line v equal to 0, for instance. So it is just going to oblique coordinates, nothing more than that, a linear transformation which keeps the origin unchanged, and then you have oblique coordinates. Now how do oblique coordinates come up from rectilinear coordinates? Obviously you should shear the axis, and now my statement is any 2 by 2 matrix of the form A, B, C, D can always be written as a combination of three kinds of transformations. One of them is a rotation, a plane rotation. So let us pictorially draw this. How do I get to these axes from the Cartesian axes? Well, if you start here and you take a little square here and you rotate this square, a rotation matrix which is an orthogonal matrix, 2 by 2 orthogonal matrix with determinant +1, then this shape is going to look like, this is what it is going to look like in the rotated coordinate system. And now you could also dilate, you could also magnify one direction and contract the other direction, for example. You can always change the scale of x and y. If you did that, this picture would perhaps look like after you change the scale in the x direction and the y new coordinate directions, it would look like this. And finally you could shear the whole thing, and then this would look like this fashion. This is the most general distortion that you can inflict on a square, small square here when you start off. So if I start with a square in the xy plane and change coordinates to ax plus by, cx plus dy, this square would get distorted into a shape of this kind. There is no reason why this should have the same area, because there is no reason why A, B, C, D, this matrix should have determinant 1. If it had determinant 1, then the area is preserved, but in general the determinant is some number which we have taken to be non-zero, and then it would in general look like this. So my statement is a general linear transformation in the plane which leaves the origin unchanged, a linear homogeneous transformation, can be thought of as being made up of a rotation, a dilation and a shear. Now we must fix parameters, we must make sure we have the right number of parameters. A general matrix looks like this. So I start with xy and I go to ax plus a b c d applied on xy, which gives me these two combinations. Now how many parameters are here? 4 parameters, 4 real parameters, and we have assumed AD minus BC is not equal to 0, so the mapping is not degenerate. So whatever we do, however we write this matrix as a succession of transformations, we must make sure that the number of parameters hasn't changed. It should still be 4. How many parameters do you need to specify a rotation on the plane? 1, just an angle, some angle alpha. How many do you need to specify a dilation of this kind? You contract one direction, expand the other arbitrarily, so there are 2 more parameters. So 3 are gone there, and finally you need 1 more to tell you through what angle do you shear. You shear one of these directions, so hold this fixed and shear, and then the question is through what angle do you shear. So there is 1 more parameter, and therefore the same 4 parameters. This is not a unique decomposition. You can do this in many ways. You can do this in different orders and so on, but the number is fixed. So let me write this down as an aside. General linear transformation, linear homogeneous transformation, because I shouldn't change the origin. I am not adding constants to the whole thing. I am not saying you have the new coordinate is ax plus by plus alpha and cx plus dy plus beta. That would mean even the origin is shifted, and I am not talking about a transformation of that kind, that is called an affine transformation, but I am talking about something where the point is fixed, the origin is fixed, and then I do the most general possible thing I can do, and this transformation can always be written as a combination of a rotation plus a dilation plus a shear. You needn't dilate both. You could say I am going to keep one of them fixed, but then you could shear about both the axes, both directions. So you could put 2 shear angles and 1 magnification or demagnification factor. It does not matter. The number of parameters is still 4. A fancy way of saying this is that the general linear group in 2 dimensions, it is called GL2R, R for reals, this has 4 parameters, and this group can always be written in terms of rotations, dilations and shears, etc. But what does it tell us physically? What does it mean? It means that once I solve this problem in which x and y have been decoupled, the general saddle point figure is going to be just a distortion of this figure here, and that distortion would mean that the most general thing I have would look like this. This would really, in the more general case, look like this. This is what a saddle point would look like in general, some distorted figure. Now the rest is detail. What the actual shape is and so on is irrelevant, but those two are in some sense topologically equivalent, in the sense that I can deform one to the other in a smooth way, and therefore once I have studied this, I do not have to study each saddle point separately. It is just a distortion of what the original simple case was. So that is the reason I said let us look at the simple cases, and then the general case is actually automatically handled. What happens if you had for example a center? Well, in a center you have these little fellows going around. You could distort it so it would look like a very strange kind of distorted oval, but it would look topologically more or less the same as the original case. What would a node look like? What was originally very neat, an unstable node for instance, which looked like this. And then similarly on this side. This picture here, again imagine taking these axes, shearing them, etc. in some crazy fashion. So you could have something which looks like this. Maybe this is the only direction, the exceptional direction, and then everything else flows from there. etc. So it's supposed to be all meeting at that point, so it will just be a distortion of the original shape. So we won't spend more time on this, because depending on the problem you can recognize whether the critical point in the 2 by 2 case is a node, a stable or an unstable node, a stable or an unstable spiral point, a center, or a unstable saddle point, and these are the only possibilities that you have. Of these, the only one that leads to periodic motion, that corresponds to periodic motion, is the center. Everything else does not have this behavior at all. But there is something more, there is something special about centers and saddle points which we saw by example, and that was whenever we looked at potentials, whenever we looked at particle moving in a potential, we ended up as with critical points which were either saddle points corresponding to maxima of the potential, unstable equilibrium, or centers corresponding to minima of the potential. This is a general characteristic. It will turn out that in what we are now going to call conservative dynamical systems, specifically Hamiltonian systems, and I will explain what that means, the only critical points possible are centers and saddle points. You can't get the other varieties which you get for what we are going to call dissipative systems. So we are now going to start making a distinction between conservative and dissipative systems. So let us do that right away in a general context and then come back to the problem of a particle in a potential. I should point out when I am doing that right away that if you had a 3 by 3 case, the kind of critical points you could have could be very different, could be quite is actually enlarged. And when you go to 4 dimensions, 5 dimensions, etc., 4 or 5 variables, it can get quite hairy. Let us look at just 3, look at the possibilities. Suppose in 3 variables the origin is a critical point, then you could have a situation which is unstable as a node, that means the flow is outwards from this point everywhere, or a stable node, everything falls in. But you could also have these crazy possibilities. If this is the x axis, this is the y axis, and that is the z axis, you could have a saddle point in which in 2 directions things flow in and in 1 direction things flow out. So that would still be a saddle point. So you could have this, and in this direction things flow out. So on this plane you would have flow like that in this fashion, and then from the other direction also you would have flow like this, etc. That would still be a saddle point. You could have even crazier possibilities, and this happens very often. You could have a situation in which 2 of the eigenvalues form a complex conjugate pair. So you have lambda 1, 2 equal to some lambda plus or minus I mu, and let us say this is less than 0, just to give you an illustration, and the third eigenvalue lambda 3 could be a positive eigenvalue greater than 0. Remember, in the 3 by 3 case with real coefficients you can have only one complex conjugate pair of eigenvalues, the third one has to be real. You can't have 3 complex eigenvalues because they have to occur in complex conjugate pairs. What happens in a situation like this? Well, if you did not have this direction, the 3 direction at all, then it is clear that you have a stable spiral point, things are flowing into the origin in the xy plane, but in the z plane they are going off. So you could have this, you start off like this and it flows in, but in the z direction it flows off. So although they spiral into this critical point, in the z direction it takes off, becomes unstable. If the system is non-linear, then you could have the following picture. This goes off a long distance and then flows out and gets re-injected into this plane and repeatedly keeps doing this, and this mechanism leads to something called homoclinic chaos. So this is a typical mechanism by which when you have higher dimensional flows you have very complex dynamical behavior. So things of this kind can happen. We will come back to some of this a little later. So let us define now what we mean by conservative versus dissipative dynamical systems. It is a useful classification, not a very significant one in certain respects, but the one I am going to make now is going to be applicable directly to Hamiltonian flows, which we will look at. Now what do I mean by conservative versus dissipative systems? Let us look at our general case. We have in mind a situation where an n dimensional system is given by a set of equations of this kind. This is not necessarily a problem of a particle in a potential or a set of particles or a rigid body or anything, just a general dynamical system, autonomous because there is no explicit time dependence in the rules here, and it is described by a set of coupled first order n first order differential equations. And our statement was that if you specify initial conditions, the future is uniquely determined in principle. Phase trajectories in the system do not intersect with each other, and if a phase trajectory closes on itself, then it is a periodic motion. So this much we know. Now what we would like to ask is a very crucial point which you are going to be very preoccupied with is, if you start at some point in phase space here and you are on a phase trajectory of this kind, and you start at a neighboring point here, perhaps due to initial resolution errors, I am really never going to be able to specify the initial point with absolute precision, then what is the future of this point here? Well, common sense would tell us that in regular systems or nice systems, these two do not really go very far apart. If you make a small error in the beginning, you stay with this error, maybe it gets multiplied by a factor of 2, but it stays where it is. On the other hand, most dynamical systems do not behave in this fashion. Nonlinear dynamical systems do not behave in this fashion at all. What really happens is, if you start here, you end up there, and if you start here, you may end up there after some time. And the future can be very, very different. The error in an initial state or the finiteness of the resolution ensures that two neighboring trajectories can actually separate as a function of time. And the question is, how fast do they separate? Well, if they separate exponentially fast in time, then there is in general no way you can compute these things, because if I start with some initial point to some error, some accuracy, and I would like to predict the future, I would certainly like to know whether I am on that trajectory up there or down here. And if the error amplifies exponentially in time, then this is not going to be computable after a certain amount of time. If at every time step the error doubles, for example, right, then after n time steps it is 2 to the power n of the original error, which you can write as e to the n log 2 times the original error. So it exponentially grows with time. Then in binary, for instance, if in the millionth decimal place you made an initial mistake, after a million iterations you are in the first decimal place. This is what chaos is, and this is why it is a serious problem, and we have to deal with it. It exists, it is very real, and most systems are chaotic in this sense, and we have to deal with it. So we will see what we should do about it. But for the moment, the reason I brought that up was because we are very preoccupied with finding out what happens to not a single initial condition, but a set of initial conditions. I start with a set of initial conditions, some neighboring initial conditions, some volume element in phase space, and each of these points goes off into a trajectory, and the question is what happens after some time to this little volume element. Now this is the question we would like to ask. Well, let us do that in the following way. So this is what x1 dot is at a given point x, and there could be a neighboring point here, let me call that x plus delta x, and I am interested in knowing what happens if you have a whole volume element here, what happens to this volume element as a function of time. Okay. Then I could also write x1 plus delta x1, the dot of that, this is f1 of x1 plus delta x1 x2 xn. So instead of x1 I start with x1 plus delta x1. Now I say okay, I have x here, I start instead of x2 I start with x2 plus delta x2 in the next variable. So and so on. So I imagine that I am here in 3 dimensions, for example. I could do this very easily. So I draw a little cube of that kind, and I call this the one direction, that the two direction, and inside the three direction. This is x, x1, x2, x3. This is x1 plus delta x1 and x2, x3 as they are. This is x1, x2 plus delta x2 and x3 as it is, and this point here inside corresponds to changing x3 by delta x3, leaving x1, x2 unchanged. So I look at each of these and write down the evolution equation for this set here. But you see, this could also be written to first order in delta x1 by Taylor expanding this function, and if I Taylor expand it, this is the original f1 of x plus a partial derivative of this function with respect to x1 evaluated at the point x multiplied by delta x1. So this is delta f1 by delta x1, delta x1 evaluated at the point x, my original point. And so for each of these. Therefore I could ask, what is d over dt of the product delta x1, delta x2, delta xn? That is nothing but d over dt of delta v, the volume element in phase space. That is just a product of all these delta x's, and I ask, what is the rate of change of that? And that is equal to this, and this is equal to, well, by the chain rule it is d over dt delta x1, right, times all these plus delta x1 times d over dt delta x2 and so on, and that we can find by subtracting from this equation the original equation. X1 dot is f1 of x1, x2, etc., and that immediately says this goes away, this function here is cancelled, and you get just this. To first order in delta x1 it says this, because the original f1 at the point x is cancels out both sides, and so on for each of these, and therefore you end up with delta f1 over delta x1 times delta x1 multiplied by delta x2, delta x3, etc. So each time the corresponding delta x obligingly comes out, and you can take that out, it's common, and this becomes delta f2 over delta x2 times delta v itself. I have rewritten delta x1 through delta xn as delta v itself. But what is this? What does this combination remind you of? Remember, f1, f2 are the components of a vector, and x1, x2 are the coordinates in phase space, and it says take the first component, differentiate with respect to the first coordinate, etc., and sum all these, and what is this called? It is the divergence of this vector field. So this quantity is nothing but the divergence is equal to del dot f delta v. Remember, the del operator is just a vector with components delta over delta x1, delta over delta x2, delta over delta xn. As you should expect, this is in fact the geometric meaning of the divergence. So when is this 0? When can you assert that an arbitrary volume element in phase space for a given flow really does not change in volume? That volume remains the same when the divergence of f is identically 0. So if this vector field f has 0 divergence, then you can assert that the volume element does not change, and I would call that a conservative dynamical system. It preserves the volume in phase space. In phase space always. elements are preserved, and I would call this a conservative dynamical system. That is my definition. Of course, in mechanical context you are more used to saying that the energy is conserved, and we will see how that is connected to this a little later. It is connected in a little intricate way, but that is just one kind of conservation. Mechanical systems could have other conservation laws, could have angular momentum could be conserved, linear momentum could be conserved, and so on. The energy is very, very special, as we will see, and the conservation of energy in Hamiltonian systems, it is directly linked to the fact that volume elements in phase space do not change, and we will see that. But this is in a general context, we have not even talked about mechanical systems. I would like to define a conservative system as one for which this vector field f has zero divergence identically. What happens if you look at the simple harmonic oscillator, for instance? Would you think that conserved? We have to check this, we have to specifically see whether this is true or not. I would expect that in potential problems things are conserved, so let us see if this is true in phase space. I have not defined my phase space too well for that purpose, but let us see what happens. You have x dot equal to v and mv dot equal to f of x, which is minus v prime of x for a potential problem, and the question is a volume element conserved in this case or not? What would you say? Well, in this problem x1 is just x and x2 is v. This is f1 and you have to differentiate it with respect to x. Does it have x dependence? No, there is no x dependence, it is v, it is an independent dynamical variable. Does this have any v dependence? So each of these terms is 0, this is 0, that is 0, and of course it is conservative. This is trivially so, it is trivially conservative. I put in a little bit of damping, what happens then? Remember, the damped harmonic oscillator was written in this form. What happens now to this divergence of f? Yeah, the second term minus m gamma v has v dependence and you have to take its partial derivative with respect to v. What happens then? Minus, very important, minus m gamma, minus. You plug that in here and what does it say? It says d over dt of any volume element is negative, a negative number constant times delta v. What does that mean for v delta v? It shrinks to a point, and indeed this is true for dissipative systems, things will shrink, because remember that the phase trajectories now would be spirals for the underdamped oscillator, look like this and things would fall in. So if I started with a big volume element here and asked what does this set of points do, they all have to fall into this point here finally, and therefore the volume element shrinks as a function of time. The fact that del dot f is negative everywhere takes care of that. It says globally everything shrinks everywhere. Of course you can envisage cases where there are situations where in some parts of phase space things could expand, in other parts they could contract and so on. That would not be a conservative system by our definition. If del dot f is identically 0, then I call it a conservative system. And I also see that if del dot f is indeed negative everywhere, then things are really shrinking. This must be a very dissipative system, things are shrinking into some point. Let us look at an example very far removed from mechanical examples, just for an illustration, and see what happens here. This is a very, very simple model, but it will tell us why we should expand our definition a little bit. I should mention that del dot f not equal to 0 I call a dissipative system, and in general I am going to be interested in del dot f negative, meaning contraction, because if things expand, if the phase space is finite, they can't go beyond the boundaries in any case, unless the phase space is infinite, in which case things could expand forever, but that is not so interesting to me. So we are going to always worry about cases where you have dissipation, things would shrink for instance. But I must warn you right away that in general a complicated system would have some regions of phase space where things could shrink, other regions it could expand, and yet other regions where things could move in a very complex way. Let us look at another problem, another example. This is called the Lotka model. It is an extremely simple model of population dynamics, and it has to do with two species of animals which are supposed to have sufficiently large numbers that you can write down differential equations for their population as opposed to difference equations, because a population is always an integer, a non-negative integer, but I am going to pretend that you have large numbers and therefore you could write down differential equations for these populations. Let us call them, in a typical case, foxes and rabbits. So you have rabbits running around, and as you know rabbits have a proclivity to breed, and let us call the population of rabbits at any instant of time x, and x dot is then equal to going to grow. If there is plenty of grass and they eat grass, there is plenty of grass, they would grow, and they would grow at a rate, at a certain birth rate alpha, depending on the current population x, and this is exponential growth. So the solution is going to be e to the alpha t times x at 0, and any positive x of 0 is going to lead to an explosive growth. On the other hand, suppose there are foxes, and let us call them y. These foxes do not eat grass, they eat rabbits, but if there are no rabbits around, then of course they would just die, and the death rate would be some gamma y. So we can draw a phase diagram in this problem. We really need only the first quadrant because populations can't be negative, but mathematically you can look at both positive and negative x and y, and it says it would just come down here and these fellows would just grow off, and this already suggests that this is an unstable equilibrium point, because infinitesimally near it things flow out. Now we put a coupling between these two and we say yes, yeah. Well, I am saying that foxes, if they do not have any food, would die out.
It will be a function of time only. Why would it depend on y?
The total number of, the rate at which the population decreases would depend, if there is a death rate 2 per 100 and the population is 2000, then the death rate is going to be, the number of deaths is going to be the rate multiplied by the current population, right. So this is the rate at which the total population is decreasing, and therefore it is proportional to the current population multiplied by some constant death rate if there is no interaction at all. So this is what the phase diagram looks like. But now let us suppose that the foxes are allowed to eat the rabbits, then clearly the rabbits are going to suffer a loss, so minus sign, and it is going to depend on how many foxes there are, but the rate at which it is going to happen is going to depend on how many foxes there are. The more foxes, the faster the rate of depletion. Therefore this is some beta times xy. The rate of depletion of foxes, of rabbits here, is going to be beta y. It is going to depend on y in this fashion. Similarly, these are going to increase now because they are able to eat, and this is going to be some delta xy. The rate at which they grow is delta x. So these are two species, it is called the predator-prey model. And you can now see a coupling has been introduced between them, and the question is, where are the equilibrium points, if any? 0 is certainly an equilibrium point. And now by our rule, if you linearize near 0, it means you throw away the nonlinear terms, keep only these terms. Then since all these rates alpha, beta, gamma and delta are positive by definition, it is clear you have one positive eigenvalue, one negative eigenvalue, and therefore this must be a saddle point here. This is a saddle point. The question is there any other critical point, and if so, what is it like? What does it do? And let us make life simpler. I am going to leave you to analyze the more complex problem, and put all these constants equal to 1, just for illustration, put all these constants equal to 1, and then you could write this as x times 1 minus y, and you could write this as y times x minus 1. So are there any other critical points? Are there any other values of x and y where the whole thing vanishes? 1 comma 1, 1 comma 1 is a critical point, so you have another critical point here. Now we'd like to know what sort of critical point is it, and what you should do is to actually linearize about that point. So you should really say, I am going to look to first order, I must find this matrix L. So the way I do it is by saying, alright, let u equal to, let x equal to 1 plus u and y equal to 1 plus v. So I shift my origin to this point here and then ask, what do the equations look like in this case? What does it look like? Well, let us write this as x minus xy, and this becomes 1 plus u, well let's leave it in the original form, x times 1 minus y is equal to 1 plus u multiplied by 1 minus y, which is minus v. Therefore this is equal to x is 1 plus u and 1 minus y is minus v, so u minus v, and this is equal to, this is minus y, so minus 1 minus v, y is 1 plus v multiplied by x minus 1, which is u, equal to u plus, sorry, u plus uv, and this is u minus v minus uv. It has to be nonlinear, you can't just make a linear change and then get a nonlinear set into a linear one. So there are these higher order terms. Okay, now what does u equal to 0, v equal to 0 look like? So here's the u axis, v axis. What does the flow look like near it? Near this point in this immediate vicinity you have u dot, because x dot is the same as u dot, it is just shifted by a constant, is minus v, and v dot equal to plus u. Linearizing. Now the matrix L, so this says L equal to 0, minus 1, 1, 0, and what are the eigenvalues of this matrix? Plus or minus I, plus or minus I. That is a pure imaginary set of eigenvalues. So what kind of critical point is it? It is a center, it is a center. So what do the trajectories look like in its vicinity? They look like little circles, because you can integrate this set of equations, by the way, it is trivial to integrate, because you write dv over du is u over v, it gives you u squared plus v squared as a constant or something. They are circles. In which direction do the circles go? Would they go clockwise or counterclockwise? They have to have continuity with this. In between, it is true that you found this in the vicinity of that point, but there is nothing else in between. So it is clear that they must have continuity with this, and therefore they have to go in this fashion. There is no option, you can't suddenly change directions between. Of course, as you go further away from the vicinity of the critical point at 1 comma 1, the orbits no longer are circles, they would get distorted, but they can't cross each other. So what it is telling you is that no matter where you start at this point, I start with a very large population of foxes and a very small population of rabbits, the foxes start dying, there is not enough food. So they come down, they die, but as more foxes die, the rabbits become, they have greater impunity, they start growing, and therefore the rabbits expand for a while, but then they get so far away that the foxes start eating them once again, and it goes up in this fashion. And then of course they eat too much, and therefore the rabbits are depleted and they come back. So the full face portrait is a very irregular set of curves, but they are periodic. It is not trivial to show that this is true, but I leave it as an exercise, and we will see a little later that you can show this very elegantly that this is indeed true. This is what the phase trajectories would look like with modulo some distortions. So there is a center here and there is a saddle point here. This oscillation was seen in the catch of 2 species of fish in the 1920s by fishermen in the Adriatic Sea, and then the mathematicians Vito Volterra and Lotka solved this problem, and they realized this is what is going on. They solved this set of equations and showed that this is the phenomenon, that really you have this oscillatory behavior. The population of the predator and the prey, they are out of phase by a fixed amount here. You can see that when one is large, the other is small, and so on, they are out of phase, and the reason for it is precisely buried in these equations. Now is this a conservative system? Oh, by the way, mathematically you can solve this set of equations for the remaining values of x and y also. Nothing very interesting happens. This guy here just looks like this. There is just a saddle point here, and then the interesting point is this 1, 1. That is a point of coexistence. That is the point at which the critical value of foxes and rabbit populations, at which they can actually coexist. You have the right number being eaten and the right number of foxes dying, and things can exist. Even though there is conflict between them, there is peaceful coexistence possible here. We have not included many facts. This is the simplest possible model. We have not included competition among the foxes for the same food. We have not included competition among the rabbits for the same food, for the same grass, and so on. So if you included competition among the rabbits, there must be a minus constant times x squared at the very least, and similarly here too there would be a competition, there would be a minus something times y squared. So that is predator prey interaction together with competition and so on. Then things get much worse. There is no instantaneous response. Once the population of rabbits increases, it takes a while for the fox population to catch up. So really the fox population's growth rate would depend on the rabbit population at a slightly earlier time, and the foxes have to eat them, they have to mature, they have to mature to the breeding stage, and so on. So the problem is actually much more complex, much more complex, but already it tells you in this simple instance that things can get quite interesting. Is this a conservative system? Well, we need to find out. We need to take this, so you have x minus xy and you have minus y plus xy, and what is del dot f equal to? It is the derivative of this with respect to x, that is 1 minus y, plus the derivative of this with respect to y, that is 1 minus 1 plus x, that is equal to x minus y. So is it conservative? Not in the strict sense of the word, it is not, but if x is equal to y, namely on this line, it is certainly true that the divergence vanishes, but that is not enough because the trajectory intersects that line only twice. But then on the average it is conservative, because for every volume element in which x is bigger than y, it grows, del dot f is positive here, there is a corresponding volume element there where it is negative. And therefore over a full cycle, if you started this little volume element and followed it as you went along here, on the average when you integrated it out, it would be 0. So you have a slightly more general definition of a conservative system. If it is periodic motion, which in this case it is, then you should really in fairness look at the volume element as an average over a full cycle. Then if it is 0, you would still say it is conservative, not in the rigorous sense of the word, but certainly for all practical purposes you could regard it as conservative. A little later I will show that this system, by changing variables, actually is a Hamiltonian system, and the fact that you have a center and a saddle really tell you that it is writable as a simple Hamiltonian system, not a conventional one, but it's writable in that form. You could now ask what happens if I have 3 species and I generalize this Lotka-Volterra model, then the matter is not so simple at all sorts of possibilities open up. Yes.
So what does being conservative mean in terms of Fox's sometimes? Could we have expected it to be conservative or not?
No, I don't think so. No, not to start with. It's just that this problem with these constants is so simple, it's so symmetric, it has this wonderful symmetry about x, about the 45-degree line. That's the reason for this special feature of this problem here. So it's not very significant in that sense, but it's significant in the following sense. If a system is a Hamiltonian system, which I haven't defined, then it's by definition conservative, and you might wonder why this system, which is closely related to a Hamiltonian system, turns out to be non-conservative, and the answer is it's due to the changes of variables. So effectively whatever you start with, every point here, every point in the phase plane in the positive quadrant lies on a periodic orbit, and across a full cycle the volume element does not change. There may be some regions where one of them is winning, the foxes are winning, there is another region where the rabbits are winning, but overall nothing much happens. So it is in that sense I specified this. So I pointed this out because this distinction of conservative and dissipative systems is a matter of convenience. It is a matter of convenience. Sometimes it has deep physical significance, and we will see why that is so. I should point out that the fact that del dot f equal to 0 tells you that the flow in phase space is like that of an incompressible fluid, and this is worth appreciating, because a fluid flows according to the Navier-Stokes equations, and now if you write it down in the simplest case and you write down the equation of continuity for this fluid, so let us do that in half a second. In real space a fluid flows with no sources and sinks in this fashion. The divergence of the current is 0. This is the equation of continuity for a fluid. It says in any volume element whatever comes in must go out, or else the density changes. So this whole thing is, it's just a balance equation, nothing more than that. Now suppose you have an incompressible fluid, rho does not change, it is constant in space and time, then this term is 0 identically, and del dot j is 0. But what is j? It says del dot, it is rho times the velocity v equal to 0. But rho is a constant, so this implies that del dot v equal to 0. Right? And our f was just the velocity of points in phase space, the phase space velocity for the flow in phase space. So this is the reason why one says that a conservative dynamical system, the flow in phase space is similar to that of an incompressible fluid in real space, for which del dot v must be 0. That is the analogy. So very often you would see this written in textbooks, that the flow looks like this, they state what is called Liouville's theorem in Hamiltonian dynamics and say this looks like an incompressible fluid. Well, the reason is this, just this. But remember that the flow we are talking about is in phase space already, it is not physical flow of a fluid or anything like that. But this has its uses and we will see what they are.